Welcome to section 910, where we're going to talk about the Taylor and Maclaurin series. So the definition of a Taylor series is f of x equals the summation of n equals 0 to infinity of f, what looks like it's raised to the nth power a over n factorial times x minus a to the nth power. But what this notation really means is this is going to be our number of derivatives that we take. So if this is a 0, that's your normal f function with a substituted in. If it's a 1, that's your first derivative. If it's a 2, the second derivative, third derivative, fourth derivative. So as you can see is how it's defined here. Here's f of a, that's when n equals 0. Then it's the first derivative of f of a over 1 factorial times x minus a to the first power plus the second derivative of a over 2 factorial times x minus a squared, so on and so forth. So this equation, or this series up here, is called the Taylor series. It's the Taylor series of the function of f at a or about a or centered at a, however you want to write, just like we did before. But for special cases when a is equal to 0, then the Taylor series becomes this equation, which basically means it's now x to the first, x to the second, and so on. And this is called the Maclaurin series. All right, so we have these two special names for these series. So first example 1, find the Maclaurin series of f of x equals e to the x and its radius of convergence. Okay, so here's the beginning of my Maclaurin series by definition. What I need to do first is I need to find a bunch of these derivatives here so I can see the pattern. So when n is equal to 0, we're looking at your original f of x, which is e to the x. And okay, e to the 0 power is equal to 1. When n is equal to 1, the first derivative, that's just e to the x. And if I put 0 in for the first derivative, e to the 0 is still 1. Second derivative, no change. Second derivative of, the derivative of f prime, which is e to the x, is just another e to the x, and you plug in a 0, and the pattern continues on forever. So these numerators here are all going to be 1. So if I were to start writing this out, like I said, my numerator is now a 1. And so this changes to the summation of now just x to the n over n factorial, starting with n equals 0 to infinity. So put in a 0. X to the 0 is 1 over 1 factorial. That's a 1. Now plus x to the first over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial. And that continues on. So this would be my Maclaurin series. Now to find my radius, I have to do the ratio test. So take your sequence function and find it a sub n plus 1. So x to the n plus 1 over n plus 1 factorial divided by the original a sub n, or in this case, multiplied by its reciprocal, n factorial over x to the n. We can do some reducing and canceling. X to the n will go into x to the n plus 1. X times, you have 1x left over. This becomes n plus 1 times n factorial. The n factorials cancel, leaving us x over n plus 1. But when the limit as n goes to infinity, x doesn't change. This is getting bigger, so we are heading towards 0, which is less than 1, which means this converges for all x. So my radius of convergence is infinity. All right. Okay, next, let's consider our Taylor series by its definition, and let's look at what we call the Taylor partial sums. And this is something we did earlier when we were converging from -1 to 1 and how we saw how our power series was really matching up with 1 over 1 minus x. So for example, if we look at our f of x, which is e to the x equals the summation of n equals 0 to infinity, which is x to the n over n factorial, let's start to find some of our sums here. All right, so e to the x, again, that's the graph here in red. And so t sub 1 of x is going to be this straight line because t sub 1, that's going to be 1 plus x to the first over 1 factorial. So we have to put in a 0, that's the 1 over 1, and then x to the first over 1 factorial. T sub 2 of x, then we add on the x squared over 2 factorial. T sub 3 of x, 1 plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. And what you can notice here is my graph, again, in red, begins to get a lot of overlapping in a short space, and then it starts to increase and a little bit each time. And again, so here's my Taylor polynomials and their partial sums starting to match up with that y equals e to the x graph. But again, if you notice this left and right hand behavior with these polynomial functions, they're going to keep bouncing back and forth, going up and going down. So again, this is only going to work in our interval of convergence from our -1 to 1. Okay. Example 2, find the Maclaurin series for f of x equals cosine of x. All right, so again, oops, that's my Taylor series. If I go back a little bit further, we need this definition right here. So again, we have to find our derivative values. So now with cosine, the original cosine function, we put in 0, f of 0, so cosine of 0, think about that's on the unit circle at 1, 0, that's the value of 1. When n is equal to 1, we're going to take the derivative of cosine of x, that's negative sine of x. Put 0 into our negative sine function. Well, at 0, then our sine function is 0, and negative 0 is just 0. When n is 2, now we're going to look for the second derivative. Okay, so let's take the derivative of negative sine of x. The derivative of sine of x is cosine of x. Keep the sign the same. Well, wait a minute. When we had f of 0 into cosine, that was a 1. So f double prime of 0, cosine of 0 is 1, but now multiplied by a negative gives me negative 1. When n is 3, okay, the third derivative, the derivative of cosine x is sine of x. Oh, wait, check this out. Cosine of x was negative sine of x, so negative negative sine makes that a positive. And again, we've already evaluated sine of 0. That was 0, so it stays 0. N equals 4. Fourth derivative, the derivative of sine of x is now cosine of x, and we're right back to when n was 0. We're back to a 1. So what's happening here is we're going to create alternating sines. Now this one's going to be a little bit more work because here every odd derivative we're going to end up with a 0. So as I write this out by definition and I start putting in my derivative values, f of 0, that's a 1, but my f prime, remember I said all the odd derivatives, or all the x's to the odd powers, or the odd factorials they're going to come out to be a 0 right here. Well, 0 times anything is going to cancel. So this term's a 0, this term's a 0. The next one over here, f, the fifth derivative would be 0. So I have 1, then a -1, then a 1. So here's what my new terms would look like if I expanded this. 1 plus 0 minus x squared over 2 factorial plus the 0. Again, we're going to drop these off when we rewrite this out. X to the 4th is positive, x to the 6th negative, x to the 8th positive, x to the 10th negative. So here's my new series. So I'm going to rewrite my summation notation. All right, the summation at n equals 0 to infinity, -1 to the nth power, because again, we want the first term to be positive. So 0 goes into -1 to the 0 power. That guarantees my positive. 0 for a power, 1. 0 times 2, 0 factorial 1. So everything stays a 1. When n is 1, that gives me the negative. Now 2 times 1 is 2. And 2 times 1 is going to be 2. So this 2n guarantees that I have all these even numbers for my powers and my factorials. I just have to have -1 to the nth power to keep my signs alternating. If we were to find capital R doing the ratio test, -1 to the n plus 1, again, we're adding 1 to every n. So got to be careful here because this is 2 times n plus 1. So this is 2n plus 2, 2n plus 2. When we go ahead and cancel and reduce, 2x to the 2n is going to leave me an x squared. And 2n plus 2 factorial will break down to 2n plus 2 times 2n plus 1 times 2n factorial, and will cancel. So the limit here, -1, becomes positive. The bottom is going to get bigger while the top stays the same as 1, or just x squared. So again, we're approaching 0. That's less than 1. And again, this converges for all x with a radius of infinity. Now, what's kind of neat about these Maclaurin series is don't recreate the wheel when they ask you a question that deals with a cosine in it. So for example, in number 3, it says find the Maclaurin series of f of x equals x cubed times cosine of x. Well, wait a minute. We just found the Maclaurin series for the cosine of x. Just multiply an x cubed to it, and then multiply an x cubed to your summation. Well, x cubed times x to the 2n power, multiply like bases, add their exponents. It's now x to the 2n plus 3, and you got it. You're done. So we'll stop here, and we'll pick up again in part 2.